So Py at Yj would be called marginal probability mass function. Marginal probability, discrete marginal density function you can say, marginal probability mass function also you can say. Two different names, mass function of y, by the way, because I am doing it for the y. Now coming to the next important definition in two-dimensional random variables, conditional probability function. What it is, let's define it. Once we define and clear with the definition, then problems can be easily done. Now, let capital X and Y be a discrete two-dimensional random variable. Then the conditional probability or conditional probability mass function of X. We should be saying conditional probability mass function of X given Y. Condition is that Y is being given to us. What's the conditional probability of X that we are being asked? That would be called conditional probability mass function. Okay, conditional probability mass function, that will be called. If Y is known, how do you find X? First thing is we should know the notation denoted by f X slash Y. Okay. Of course, in the bracket also small x slash y you will be writing. It's defined as P of X slash Y in the bracket small x y. This is equal to P of X is equal to X comma capital Y is equal to Y by P of Y is equal to Y. Capital X slash Y is nothing but probability of X if Y is known. Given Y, or if Y is known, how do you find it? That's been asked. Since Y is fixed, you'll be changing X values. I can as well write this as Xi also. What that is 1 by P of capital Y is equal to Y. P of capital X is equal to Xi, because X is only changing, Y is fixed. I can rewrite this as well like this. Okay. Now, also the other version also let us write. This is conditional probability mass function of Y, this is. Of X, this is, provided Y is given. Similarly, the opposite one. Conditional probability mass function of Y given X. That also let us write. Conditional probability mass function. Probability mass function P Y X. Y by X. What it is? Mass function of Y given X. Given a capital X is equal to X. Okay. Yeah. So what that would be is P of Y slash X, small y slash small x. This is equal to P of capital X is equal to X, Y is equal to Y. What's been given to us? X is equal to X is being given to us. Also, I can rewrite this as 1 by P of capital X is equal to X into P of capital X is equal to X comma capital Y is equal to Yj. Okay, of course, the condition is the denominator should not be 0, guys. Here I should write if P of capital Y is equal to Y is not equal to 0. Here I should write that. And then here I should write that P of capital X is equal to X is not equal to 0. Okay, given that. Okay. This is it about conditional probability mass function. The word is conditional probability mass function, guys. Now, there is a necessary condition. See, I know already. If you know already what that is if I use a word, one word, that is, if there are mutually exclusive events, you know that, right? Mutually exclusive. What are mutually exclusive events? If I'm talking about probability and say there are two mutually exclusive events, means what? One is independent of the other, or in other words, conditional probability in one dimension, I'll be writing like this. Just see here, guys. What that is P of probability of B given A. If I'm being asked, how will I find it? P of A intersection B by P of A, yes or no? Or I'll rewrite it like this. A intersection B. That means what? I want A and B both to happen. That would be what? P of A into P of B by A. See, if I'm picking up from my pack of cards, I'm picking up two cards, one after the other. If I'm doing it without replacement, then they will be dependent events. Okay. Without replacement, this thing will happen. If I'm replacing the card back, the total probability doesn't change. The card I'm expecting probability also doesn't change. In such a case, you will call this to be P of A into P of B only, or in other words, you will say here A and B are mutually exclusive. Yes or no? The same thing is spoken about in a different way, guys. That's it. A different notation when two-dimensional variable is there. What that is see, both the discrete random variables are, if I will write the condition here, x and y are independent, then how will this be? How will this conditional probability be? Very simple. How will that be is, the conditional probability of this discrete random variables will be P of capital X is equal to xi, y is equal to yj. This is equal to P of x is equal to xi into P of y is equal to yj. No dependence. Okay. They are not independent. So each probabilities are calculated separately. That means what? I can as well say from the basic definition that if they are defined on different sample spaces, like I was talking about, if x and y in the beginning, in the first video, if x and y are on joint probability, if x and y both are defined on the sample space, I will make a mention of it. If they are defined on different sample spaces also, they are independent. Okay, similarly, if they are independent also, then the probabilities would be something like this. And then this yi and yi gets cancelled off, or xi and xi gets cancelled off. It's all about finding out only one probability with the conditional probability. Okay. Yeah, that's it. I will talk about problems in the next video on conditional and probability and marginal distributions.